Welcome, everyone. Today we're doing a deep dive into something really fundamental, the core ideas behind arc welding.
That's right.
We've got some great source material, articles, notes, and the plan is to really pull out the essentials. You know, how the arc actually works, how heat is managed, that's critical, the parameters you adjust, and the different power sources involved.
Yeah, it's about getting behind the sparks and understanding the mechanics.
Exactly. Think of this as your shortcut to grasping how you actually create a strong, reliable weld.
Okay, so where should we start? The arc itself seems logical.
Definitely. All these main processes mentioned, MMA, TIG, MIG, MAG, SAW, they all hinge on creating this arc, right?
Absolutely. That's the common thread. It all begins with getting an electrical discharge across a gap.
Okay, so between the electrode and the metal you're welding.
Precisely. You need a high enough voltage across that gap. That's your open circuit voltage. We'll get more into that later. High enough to basically cause a breakdown, creates a spark.
Like a tiny lightning strike.
Exactly like that. And that spark is super intense. It instantly heats up and ionizes the gas around it.
Ionizes meaning. Makes it conduct electricity.
Yeah, it turns the gas into a plasma, which is, well, conductive. Once you have that conductive path, the main welding current can flow across the gap.
Ah, okay.
And that sustained flow of electrical current is the arc.
Got it. So spark starts it, creates the path, current flows, and that's the arc. And its main job is just heat.
Purely generating heat. Massive amounts of focused heat, right where you need it to melt the base metal edges.
And usually melting the electrode, too.
Usually, yes. That's a key point from the sources. In MMA, MIG-MAG, SAW-W, the electrode itself melts. Little droplets transfer across the arc into the wood pool. It gets consumed.
But not TIG.
Right. TIG's the exception. It uses a tungsten electrode that's non-consumable. It just provides the arc, the heat. If you need filler metal, you add it separately, like feeding a wire into the pool.
Okay, that makes sense. Arc is heat, and often the filler material source, too. But, like you said, managing the heat is the real trick, isn't it? And productivity comes into play here.
Big time. How fast you can lay down that weld metal, your deposition rate, that's huge for productivity, and the sources are clear. Welding flat, the PA position, usually gives you the highest deposition rates.
Why is flat so much better for speed?
It's mostly gravity, really. Welding flat, you can manage a bigger puddle of molten metal. It doesn't drip or run away like it might vertically or overhead.
Right.
So for those consumable processes, deposition rate is pretty much tied to current density. More current, more wire melts.
Makes sense.
And even for TIG, higher current means more energy to melt the base metal, so you can add your filler wire faster. The flat position just makes controlling everything easier at higher speeds and currents.
Okay, so speed, deposition, productivity. Which leads us straight into this concept the sources really emphasize, heat input. How's that different from just, say, arc energy?
Good question. Because they're related but distinct, arc energy is the raw heat the arc generates per unit length of weld.
Okay.
The formula they give is arc energy equals volts times amps divided by your travel speed.
Simple enough.
Mostly, yeah. But you got to watch the units for speed. It needs to be in millimeters per second for the standard kJ/LM unit. If you measure in millimeter per minute, you have to divide by 60 first.
Right, unit conversion. Okay, so that's arc energy. What's heat input then?
Heat input is the energy that actually gets into the workpiece per unit length. It's the arc energy multiplied by a thermal efficiency factor.
Ah, because some heat is lost.
Exactly. Lost to the air, radiation, spatter, you name it. Not all the arc's energy actually contributes to melting the metal you want melted.
And the sources gave specific factors for these losses.
They did. SAW is apparently very efficient, factor of 1.0, so pretty much all the arc energy goes into the weld.
Wow.
Yeah. Then you've got MMA, MIG-MAG, flux core. They're typically around 0.8, so 80% efficient. TIG and plasma are a bit lower, around 0.6. More heat escapes relative to what the arc generates.
Let's quickly run through that calculation example they had. A mag weld, 24 volts, 240 amps, moving at 300 millimeters per minute.
Okay. First, speed conversion. 300 millimeter is 5 millimeter sec, right? 300 divided by 60.
Yep, 5 millimeter sec.
So arc energy, 24 V240A, 5 millimeter sec, that's 5 millimeter 60 divided by 5, equals 1,152 joules per millimeter.
Or 1.152 kilojoules per millimeter. The source rounded it to 1.2.
Yeah, 1.2 kilojoule millimeters common. That's the generated energy. Now, for heat input, MAG has that 0.8 factor.
Right.
So heat input equals 1.2 kilojoule milliliters times 0.8, which is 0.96 kilojoule milliliters.
Okay, that really clarifies the difference. Arc energy generated, heat input actually transferred.
Yeah.
And the sources kept saying the main thing controlling heat input is travel speed.
Absolutely critical. Look at the formula speeds on the bottom. If you go faster, heat input drops. If you slow down,
Heat input shoots way up.
exactly, even small changes in speed have a big impact.
And this connects back to welding position, doesn't it? Because the position dictates how fast you can realistically move.
Precisely. Think vertical up welding. You have to go slow, often weaving side to side, fighting gravity. That slow speed means really high heat input.
Right.
But vertical down, gravity helps pull the puddle down. You can zip along much faster. Result, low heat input.
And horizontal, overhead.
Horizontal vertical often limits weaving, so speed stays up, HI stays low. Overhead, you need lower current anyway to control the puddle, and you move fast, also low HI.
So flat is the only one where you have real flexibility in speed and therefore heat input.
Pretty much. You can run flat really fast for low HI or slower with higher currents for very high HI, depending on the job.
So position fundamentally constrains your speed range, which sets your potential heat input range.
Mm-hmm.
Do different processes also have typical HI ranges?
Yeah, definitely. SAW, often being automated and used for heavy stuff, can easily reach very high heat input levels.
Okay.
Whereas TIG and often MIG-MAG are capable of really low heat input. That's super important for thin materials or metals sensitive to heat. The sources mentioned, a typical controlled range is maybe 1.0 up to about 3.5 kJ/mm.
Fascinating how it all connects. Position, speed, process, all funneling into this heat input number.
Yeah.
Okay, so we understand the arc, the heat, measuring it. What about the knobs we actually turn on the machine? The parameters?
Right, your direct controls. Arc voltage is a big one.
What does changing the voltage do?
Voltage is directly tied to arc length, how long the arc is. So in processes where the machine controls voltage, SAW, MIG-MAG, FCIW, changing the voltage setting changes that length.
How does that affect the weld?
Higher voltage means a longer arc. It tends to spread the heat out, giving you a wider, flatter weld bead.
Okay.
Lower voltage, shorter arc concentrates the heat more, makes the bead narrower, maybe piles it up more, and can increase penetration. And for MIG-MAG specifically, voltage heavily influences how the metal transfers across the arc spray, globular, short circuit.
Okay, so voltage is width, end shape, and metal transfer. What about welding current?
Current is generally your main control for penetration depth. How deep the weld fuses into the base metal.
Simple rule.
Pretty much. Higher current, deeper penetration.
Why is controlling that depth so critical?
It's all about dilution. That's how much of the base metal melts and mixes into your weld puddle. If you're joining different types of steel or putting down a stainless layer on carbon steel, you need to control how much base metal mixes in, or you won't get the final weld properties you need.
Right. Too much mixing can mess up the chemistry.
Exactly. Penetration control is dilution control.
Makes sense. Okay, voltage, current. The last big one is polarity, right? Positive or negative.
Yep. Polarity determines where most of the arc heat is focused. Is it concentrated more on the electrode tip or on the surface of the workpiece? And this changes depending on the process.
Okay, let's break that down based on that table in the sources. For MMA, stick welding.
Okay, DC electrode positive DC plus V puts more heat into the work. That gives you the best penetration.
Gotcha.
DC electrode negative DCV puts more heat into the electrode, so less penetration, but it melts the electrode faster, giving a higher deposition rate. Good for filling gaps or overlaying, maybe.
And AC.
Alternating current is mainly used to combat arc blow. That's a magnetic thing that can deflect the arc. But not all stick electrodes run well on AC.
Okay. How about TIG?
TIG is almost always DC electrode negative, DCV, because you don't want to melt that tungsten electrode. Putting the heat into the workpiece is key.
But there was a big exception.
Aluminum and magnesium. For those, you have to use AC. The alternating current has this cleaning action that breaks up the tough oxide layer on the surface of those metals. DC just can't do that effectively.
That's a perfect example of how specific it gets. MIG-MAG with solid wires. Is that simpler?
Much simpler. Pretty much always. DC electrode positive, DC plus fish. Good stable arc, good penetration for almost everything you do with solid wire MIG-MAG. DCV is very rare. AC isn't used.
Okay. Flex cord and metal cord wires. FCA, MCEs.
Mostly DC plus V. Again, that's the standard. But some specialized wires, especially basic flux ones designed for welding in all positions, actually run better on DCV. Still no AC, though.
And finally, submerged arc.
Similar logic to stick welding, actually. DC plus V for the deepest penetration. DCV for less penetration, but higher deposition, good for buildup. And AC is quite common in ASW, especially with multiple wires, specifically to minimize arc blow issues, which can get bad at high currents.
Wow. Okay. So polarity isn't just a flip of a switch. It's really tailored to the process, the material, even the specific wire sometimes.
Mm.
Right? We've covered the arc, heat, parameters.
Yeah.
What about the box that powers it all, the power source?
The engine, yeah.
Oh.
It provides the electricity. We mentioned open circuit voltage, OCV, earlier.
The voltage needed to start the spark.
Right. It's relatively high, maybe 50 to 90 volts, just sitting there before you strike the arc. But once the arc is lit and stable, the power source operates based on its static characteristic.
Which is?
Basically how the voltage and current relate to each other while you're welding. And fundamentally, power sources are built as either constant current, CC, or constant voltage, CV.
Let's tackle constant current first. CC.
Okay, CC machines are what you typically use for manual processes. Stick welding, manual TIG. Why? Because on a CC machine, you set the current. The voltage then varies depending on how long you hold your arc length.
And they call it a drooping characteristic.
Yeah, if you plot voltage against current, the curve slopes downwards, it droops. And here's the clever part. That drooping shape means if your hand wobbles a bit and the arc length changes slightly, causing the voltage to fluctuate.
The current stays pretty stable.
Exactly. The current changes very little. And since current is the main thing controlling melt-off and penetration in these manual processes, keeping it steady, even with slight hand movements, lets a welder maintain control. The machine prioritizes constant current.
Okay. CC keeps current steady for manual control. What about constant voltage? CV.
CV is for the wire feed processes. Midmag, flux cord, submerged arc, anything with a wire feeder automatically feeding the electrode.
And how does that work?
With CV, you set the voltage on the machine. The wire feed speed you set is directly linked to the current. Faster feed needs more current to burn the wire off.
And the characteristic is flat.
Relatively flat, yes. Now imagine the wire dips slightly closer to the work, shortening the arc. The voltage tries to drop. But because the curve is flat, even a tiny voltage drop causes a big instant surge in current.
Okay.
That surge in current immediately melts the wire back faster, increases the burn-off rate.
So it burns the wire back until the arc length is correct for the voltage you set.
Precisely. It's self-regulating. If the arc gets too long, current drops, burn-off slows, arc shortens. It happens incredibly fast, so for practical purposes, the voltage stays constant at your set point.
That's clever. It automatically adjusts the burn rate to maintain the set arc length voltage.
Yep. That rapid feedback loop makes CV perfect for processes where a machine is handling the wire feed.
Okay, wow. We've gone from that initial spark through measuring heat with heat input, dialing in voltage, current, polarity, and now understanding these two fundamental power source types, CC and CV.
Yeah, we've really tried to pull out the core concepts from those sources, hopefully making sense of some complex interactions.
Absolutely. And understanding this stuff is why it matters. It explains why you choose one process over another, why position is so critical, and really what goes into making a quality weld. It's definitely not just melting metal together.
Not at all. It's highly controlled.
So here's something to think about, a final thought for you listening. Reflect on that delicate balance of heat input. It's mainly controlled by travel speed. How differently is that managed when you have a human hand trying to hold a steady arc length with a CC machine compared to the automatic super-fast current adjustments of a CV machine responding to wire feed? How does that fundamental control difference influence which process, which position gets chosen for a specific job?